Hello, my name is Tammy Freeman and I'm the editor of Medical Physics Web. I'd like to welcome you to today's webinar, Tomotherapy Planning in RayStation. The webinar will be presented by Misty Lehman-Davis, Senior Application Specialist at Research Americas. Misty will discuss how RayStation allows seamless planning for centers with helical tomotherapy combined with conventional linacs, enabling all planning to be performed within one treatment planning system. Misty welcomes your questions, so please do send in questions at any time during the webinar using the questions button on your screen. You can also rate the webinar at any point using the ratings button. Now, I'll hand over to Misty.
Great, thank you. I just want to say thank you for everyone to take time out of your busy schedules and join us for this session today. As Tammy said, my name is Misty Lehman-Davis, and I'm a Senior Application Specialist with Research Americas. I'm excited to talk about tomotherapy as I've had a long history with it. I come from a small community hospital in South Dakota where we had tomotherapy machine in 2003, and we treated our first patient in 2004. As the lead tomotherapist, it was very exciting to kind of see these complex treatment plans develop, as well as the ability to do daily adjustments to the plan. In the early 2000s, I attended dosimetry school in North Carolina. And here I continued my career at the University of North Carolina, where in 2011, I became one of the lead TOMO planners as well. At the University of North Carolina, we were able to acquire RayStation as our commercial planning system. So as the dosimetry manager, I was able to assist in the implementation of the system, where I now currently work for Research. Just a brief background, enough about me, but some people I think that perhaps Research is a new company, and indeed it is not. Research Laboratories was founded in 2000, where we wrote algorithms for many of the systems that you probably are all familiar with, such as DMPO, SmartArc, TOMO, SharePlan. And in 2010, RayStation was FDA approved, where in 2011, RSA, Research Americas, was founded. So that's just a brief little history of myself and a little bit about our company and where we come from. And I'm just super excited to be able to show you kind of the two things that have been my passion as far as the tomotherapy planning system, as well as the ability to plan in RayStation and offer this as our seamless platform. So the first version of tomotherapy planning in RayStation was released in December of 2016 in our version 6 Service Pack 1. This has gone through FDA clearance and is clinically available. The initiative for TOMO planning in RayStation is to provide the goals of providing that integrated system for our users, one platform with multiple modalities. Development's objective from the start, of course, has been for the optimization to match current tomotherapy plans in both computation speed and in delivery time. There will be further utilization of the tomotherapy treatment system in future releases. The TOMO plan import from IDMS and Plan Explorer for TOMO and TOMO Direct is set for the summer release of RayStation 8, together with planning for TOMO Direct. RayStation currently supports TOMO Helical IMRT with both the fixed JAWS and dynamic JAWS, as well as the advanced features in RayStation such as MCO, our Multicriteria Optimization, adaptive planning, and fallback planning. This is a joint project with the Accuray Development Department. So I just want everybody to be clear that we are working and collaborate together to bring the best seamless product. Utilization of TOMO planning in Research will require an up-to-date IDMS from Accuray. This is currently IDMS 1.1.1. IDMS is the Integrated Data Management System provided by Accuray. This will be supported for most of the modern TOMO machines that are up to date with the latest service pack. So which that means is we will work with Accuray to validate IDMS support for each individual machine. The take-home message really is if the machine can be used with IDMS, then RayStation can be used for planning. And it is possible to do an IDMS-only upgrade without the Accuray Precision Treatment Planning System. To start, I want to give just a general overview of how the methodology of tomotherapy works. First, we start with the positioning of the patient. You can see here that we acquire a daily MVCT scan. There's also an automatic algorithm for the registration of the reference CT to the planning CT. And this can also be fine-tuned manually by the user. You can see here that the three translations of the lateral, the longitudinal, and the vertical can be made, as well as a roll. Now the lateral, the longitudinal, and the vertical shifts are made via table adjustments, and the roll would be made with a gantry rotation. So this is the general daily routine setup that's used for patients for image-guided radiation therapy on the TOMO treatment system. Next, we move to the treatment delivery, and this is done with a 6 MV source. This is done in both the helical and direct mode. So you can see here the movie depicts the patient as he or she traverses through the bore. In helical mode, as the gantry rotates, the intensity is modulated by the leaves as they move. This is our intensity modulated IMRT. It's like dose painting because really we have so many degrees of freedom along with this narrow beam. This helps us to create some very intricate and delicate plans, if you will. TOMO is a Greek word for slice or cut, so hence we are delivering a treatment slice by slice by slice. Some key components in the tomotherapy machine is the fan beam. This fan beam has a maximum of 40 centimeters by 5 centimeters. The field width is chosen at the time of planning, and this is chosen in increments of 5 centimeters, 2.5 centimeters, or 1 centimeter, whichever your machine has been commissioned for. That's what will be available. The fan beam does not have a flattening filter. It uses the binary MLCs shown here. The leaves are either opened or closed, and they are rapidly open and closing, about 20 milliseconds for these leaves to open, and this is driven by the pneumatic system. There's also a detector at the base of the scan, and this is used for the MVCT reconstruction, as well as the SAD of the machine at 85 centimeters. If we look at the profiles then, the cross-plane profile depicted here in the middle looks like the typical shape of a non-flattened beam, and this is because, again, we do not use the flattening filter. The in-plane profile looks flat. We're looking at that 1 or that 2.5 and 2 centimeter section of the beam, and then as well as the depth profile depicted at the bottom here. The static or fixed jaws utilize 1 field width for the entirety of the plan, and this can potentially lead to more dose to an organ at risk or to the surrounding normal tissue, as well as compromise the treatment delivery time. The dynamic jaw, however, allows for a varied field width, which provides that sharper longitudinal penumbra. You can see here changing the 2.5 provides a very sharp edge, where it then allows to open up to a 5 centimeter throughout the rest of the treatment volume. If you look up at the top left-hand corner here where it says static jaws, what we see is that open field. And in order to cover the very superior part of the tumor, we have included in here an organ at risk. Whereas on the right picture, under dynamic jaw, we see that the jaw has been able to close to the 2.5, providing that sharp edge that is depicted at the bottom as well, where you see it's open. The yellow arrows, I apologize, they're a little hard to see on this, but you can see that we have included the OAR up on the left where we have the static, and down at the dynamic, you can see that that organ at risk, that critical structure up there, the chiasm or brainstem, whatever we're trying to cover, has been more adequately avoided. And the nice thing then is then throughout the duration of that target, as it is treated, we can use that 5-centimeter leaf, which will provide us with a shorter treatment time. The TOMO laser system is equipped with 2 lasers. The first is the red movable laser, and this is for patient setup. The second is the green laser, which is the virtual isocenter. While the patient table traverses through the machine with 51 projections in concert with the binary MLCs, we can see the benefits when creating these high complexity plans. So here we have quick leaf motion, thousands of radiation beamlets, and the ability to treat up to 135 centimeter field length. At the bottom, there's a few pictures here that just depict hippocampal sparing or treatments, the ability to create those donut-shaped plans, as well as really nice concave plans. Tomotherapy is used for some very specific treatments most often. I would say most often used in head and neck, the ability to do adaptive head and neck treatments. It's very nice for retreatments where we can put and block any critical structure that has already had dose. As well as here you can see that we have some pictures of plans with breast lymph nodes where those are kind of deep-seated and we want to be able to treat those. Same thing with the bilateral breast where we're able to really treat the cavity while sparing the heart and lungs underneath. It's also very nice in use for sarcomas. They can often be long, and this bodes well for that. Same with mesothelioma, where we are able to treat the lung lining while avoiding the inner normal lung tissue. And another really nice utilization of this technique is with the craniospinal axis. You can see here where we're possibly limited in conventional linacs by the length of the field, where we would have to shift an isocenter and, of course, worry about our gap shifts in between. This gives us the ability to treat seamlessly from top to bottom, as well as the use of multiple SBRTs. So the tomotherapy planning workflow within RayStation, if you're accustomed to planning in RayStation or you have access to the software, this is very similar to how we would set up our typical patients. We start here with the patient being simulated. At the time of CT simulation, we would put BBs or localization points on the patient. And at this stage, this is where we would set a point and we would mark that as our red laser. And this laser is depicted as the localization point within RayStation. Our next step in patient setup is to insert the tomotherapy table. This tomotherapy table is provided via a structure template that is easily inserted before our planning takes place. The tomotherapy workflow continues into plan design. This is where we would just simply select new plan, depicted here by our green plus symbol. In checking and making this plan, the treatment technique we would set to TOMO HELICAL, and the treatment machine we would utilize as your clinical tomotherapy machine. And we also have the ability to put in a prescription at this phase of setup. The next phase would be to add our beam. This beam is added and the isocenter is going to be located at the center of the image set by default. Of course, in RayStation, we still have the ability to center the isocenter in the middle of an ROI or to use the coordinates of any POI that we have. Once we've set the beam and found our isocenter, there's some very nice visualization tools here. You can see that the treatment and imaging field of view, as long as the bore, will be visualized in the 2D and 3D screens. The bore is the outermost circle depicted in orange, and then the field of view is the blue circle on the inside. These are just nice tools if you need to move the patient anterior or posterior. You're able to see where that patient lies within the field of view, as well as once you've done that, if you would like to turn this off under visualization in our beam settings, it's just a simple click on and off, which just provides a nice reference point for us to be able to see this if needed. In the patient setup dialog, this is where we will see the red and the green lasers. So the indication of the red lasers, which remember we set as our localization point, and the green lasers of our ISO center, this patient dialog will offer us that offset. This is transferred to IDMS at the treatment console, and this can be used every day for the automated patient setup. This offers a real nice ease of setup, as the patient will automatically be centered on the ISO center at the time of your first MVCT. Our planning workflow, we are able to set up our optimization, and this is just setting up our objectives and our constraints, and optionally using our clinical goals. Our plan optimization functions are the same as VMAT and SMLC. What is different is the beam optimization settings. So what you can see here is because we've picked helical, TOMO helical, we now have the ability to change our jaw mode, and we can change that from the fixed or the dynamic. We can set the field width, which is the 1, the 2.5, or the 5 centimeter jaws, again, whatever the machine you have has been commissioned for, as well as the pitch factor, which is user defined. This pitch factor defaults at the 0.430, but of course you can put in the famous 0.287 or any variation thereof of what you're used to planning with or what you need to accomplish for your plan. We have also presented the user with this option to set a delivery time factor. So the delivery time factor will be the time will be limited to the shortest possible delivery time multiplied by this factor. So a factor of 1 would be the fastest possible treatment with full field target coverage. Okay. I also have the delivery time where you're able to set a maximum delivery time, as well as a gantry period, both specified by the user as a maximum. Each clinic, of course, will have to find what is the right parameters and combination thereof, which is nice because we can use these in conjunction with each other. It's just whichever one is strictest, that is what will lead the optimization. Also in the tomotherapy planning workflow in RayStation, in our plan optimization settings, we have the option to protect a structure. We can protect it from entrance, and we can protect it from entrance and exit. So what this means, if we select entrance, then the beam cannot pass through this ROI to reach the target. If we select entrance and exit, then the beam cannot pass through the ROI from any direction. And this is nice, you know, in some clinical cases where we perhaps have bilateral hip prosthesis or a single hip prosthesis, and of course we don't want the beam to pass through that. Another would be if we wanted to contour out the shoulders. You know, sometimes these can be very unstable in our daily setup, so we could avoid those and choose to avoid entrance into that as well. Next, under plan optimization, in the optimization and segmentation settings, which is depicted by this little tool wheel here, we can choose to compute final dose. In computing final dose, what that will do is give us a deliverable plan. We can simply select Start Optimization once we have entered our objectives and our constraints, and we can also choose to continue this optimization. So we just recommend that you run an optimization, give it some iterations, and do a second dose calculation so that that CC dose calculation is available before you review the plan. Once we've achieved a plan, or we're at a point where we want to kind of evaluate a few things, there are some nice visualization of the control points within the RayStation platform. Here we can view the control points in the beam's eye view. This is depicted here, and you're able to see those as the gantry rotates around. You're able to see whether those control points are open or closed and kind of look at how this plan has been modulated. We also have the leaf open time diagram that's displayed here on the right. And then if you look at the bottom, this is just nice. You can really get into some fine detail of where the control point is, what the gantry degree is, and couch offset for that control point. And the export of the sinogram is supported via scripting in RayStation. So there are also some really nice beam animation. We're able to play an animation for you and provide that in the 2D, 3D, and beam's eye view, as well as the room view. You can see here, if we were playing this, we could show it in the axial, the transverse, as well as that sagittal and coronal view. We could look at those one at a time or all together. It does show in the beam's eye view, so this is just nice to watch the patient kind of traverse through that gantry head and just make sure that indeed any of our support structures that we have contoured aren't colliding and so forth, as well as again in the beam's eye view. This will show us the position of those leads, whether they're open or closed, and it does that as the patient traverses through the bore and the gantry rotates around. All of our relevant beam details are displayed, and under the beam tab here, you can see that we have the display of the number of projections. This will be the total number of projections. So we have 51 projections to cover one gantry rotation. This will give us the total of all projections used in this plan. The projection time is the time needed for one projection. We also display the gantry period need for one. Machines are based on time rather than MU, so we will show that in your delivery time in seconds. As well as the modulation factor will be displayed here under the beams tab. Modulation factor is the longest leaf open time in a plan divided by the average open time of all the non-zero leaf openings. So really this is just a number expressing the complexity of our modulation. So we've kind of talked about plan optimization, setting up a tomotherapy plan within RayStation, and now I just want to kind of tell you a little bit about some of that advanced features that we offer in RayStation that you can use for tomotherapy planning. And we do have the ability to plan with MCO. So there's this great Italian economist named Vilfredo Pareto, and I did practice his name, and he studied the economic efficiency and income distribution. And through this, the Pareto chart the purpose is to highlight the most important among a set of factors. And he came up with the Pareto principle, also known as the 80-20 rule, which simply states that for many events, roughly 80% of the effects come from 20% of the causes. So really, in essence, we can't make anybody richer without making somebody else poorer. And this kind of bodes well into the solution for radiation dose and in the trade-offs that we need. In order to make something better, of course, something else will have to get worse. Since IMRT is kind of a multivariate problem, if you will, with trade-offs, we can simply view this as a Pareto problem. And to create our solution we would enter our trade-off objectives and/or our constraints. An objective is any organ that you want to have a slider. So after we've developed our Pareto plans, we get nice slidey bars. This can be organs at risk or targets. With the utilization of EUD, this is our equivalent uniform dose, we can do that with a 0 centigrade and varying A values. We can use the minimum or maximum DVHs. And then of course, when we set constraints, these are usually reserved for our targets. These are our must-haves, our non-compromises, if you will. So of course, we can still have constraints that are an organ at risk. If we wanted to put a spinal cord in because it had had previous dose, or we're really strictly limiting dose to a structure, that could be used as a constraint as well. From here, once we've entered in our constraints and our objectives, of course, we need to build our solution space. And this is where the generation of our Pareto plans come in. Our anchor plans are generated per trade-off. So if you've entered it in the trade-off slide, what we do is we build a plan that simply gives the lowest or best possible solution for that organ at risk while keeping the target coverage. And so we build an anchor plan for each of those. Then you also get auxiliary plans, and these are constructed to improve that Pareto surface and trying to create our Pareto optimal. Once we have generated these Pareto plans, we have the ability to then navigate. This is where our navigated plans come in. It's the sum of all of our anchor plans. And really the navigation of all of our Pareto starts now. And from that point, IMRT, as we stated, as a multivariate problem, since we have objectives and constraints and we've created this space to investigate our solutions, to try to find out where we can push one thing, where does the dose go from there, now we're able to make good decisions. We can see it, where it's going. So we don't generate bad plans. Instead, you're generating a whole range of acceptable plans for each individual objective, and then we can navigate through those trade-offs to really see a plan that is best suited for us and our physicians. MCO is fully supported in the TOMO planning workflow. The workflow is, of course, just as identical to the conventional modalities that we offer. The real nice fact here is that the navigated doses can be constructed by a deliverable plan to sub% accuracy. So this really makes that helical concept an ideal treatment technique for MCO. Once we've created that deliverable plan, additional objectives and constraints can be added, and both physical and biological functions are available if we should want to do further plan optimization. So essentially, this becomes a standard optimization problem from this point forward, where we're able to add this reference function. So all of the things that we've done up to this point in navigation and finding our optimal solution, we can still, if we've forgotten to add a structure, we can certainly add it in here. If the physician would like us to push harder off of one structure or another, we can do that from here. Or if you're like me and you forgot to draw the cochleas once in a while or something of that sort, you can go ahead and draw a structure and go ahead and add it into the optimization from this point. Another feature that bodes well with the, another feature in RayStation that bodes well with TOMO planning is fallback planning. So fallback is built on a dose mimicking algorithm, and this module allows the users to create contingency plans. If the machines go down, or if we get backed up, we can quickly transfer the patient from one machine to another. An example would be taking a TOMO plan and falling back to an IMRT or a VMAT plan, or vice versa. This can be done quickly through the use of protocols where they can be created automatically. These protocols can be created automatically at the time of plan approval, and so they're just available for you at any time that you need to fall back. So this, of course, happens nicely or bodes well when we have a machine go down. We don't have to delay the patient a day or two. We can easily transfer modalities as well as combine with other plans or other fractionations. We can import any dose. So we can import brachy, TOMO, CyberKnife, you name it. We can import that dose and mimic it, which is nice for plan summations and the ability to really create consecutive plans. And of course, there is the alternate use that none of us like to talk about, but we could create these mimic plans automatically. And so this could really determine which modality is best. This is important for some states that require pre-authorization for our insurance companies. So instead of painstakingly developing multiple plans from scratch, you could use the fallback planning tool as a method to obtain that for documentation as well. We've also had some validation, of course, of our RayStation Tomotherapy platform. What we've done here is full validation against measured data and the dose computed by the Accuray Precision Treatment Planning System. If you look at the top left, this is an imported Accuray plan, and the bottom right is that identical plan taken and simply recomputed in RayStation. It's really hard to see, but there are also these 4 little green dots within the tubes there that are utilized for the measurements, as well as the comparison in the line dose. The dose differences are displayed on the right with this line dose, and you can see that those really line up well and bode well to the fact that we are trying to match both computation and delivery speed. We have users. Some of these images and pictures come from our friends in Lille, France, where they presented their findings at a RaySearch European users meeting in 2017. And really what they did was take that multi-criteria optimization and develop plans in RayStation. They didn't want to create any bias in planning, so they'd plan one first in the Accuray platform, then one in the RayStation platform. And what they were able to do is just really utilize MCO and compare and see how they liked that. In setting their goals, you can see here that they also just set their plans and their OARs. They use the clinical goals to guide them, and a lot of their organs at risk and targets were placed in the constraint side, as well as when generating PARETO plans, they used the max EUD of 0 for their organs at risk groups. They used uniform dose on their targets, and then they simply allowed their navigation to be guided by their clinical goals, and they did this in order of organ at risk priority, which they set. Here they did 6 head and neck patients, 3 breast patients, and 6 pelvis patients. And they found that all of their RayStation plans were very comparable to those that were planned in Precision Platform, and really felt that the utilization of MCO just helped push those OARs further and perhaps provide some solution or some space to navigate through that we didn't see or know existed in the beginning. Of course, after they did these plans, they wanted to make sure and do patient-specific QA. So they measured this with a 2D chamber array, and the sinogram was applied to calculate dose in the phantom. And here they found very nice correlations within their measured dose between the 2 systems. So it's just nice to see that they validated the use of RayStation. I include this slide because I think it's very interesting, and I think we've all perhaps participated in a PROKNOW planning comparison and the challenges, and they're nice to see the different techniques and uses out there. And I think that 3, if you just look at the top, is RayStation with the modality of tomotherapy. And as we utilize MCO and utilize RayStation, I hope that we can see more of those up there in our plan challenges to come. Next, we're going to move on to machine commissioning. The Accuray standard data is available in an uncommissioned machine in the RayStation physics module. This installed machine is tuned to match the data from Accuray. So this is where RayStation comes in, and the import from IDMS function is used to upload the machine-specific parameters, the ones that come from IDMS. Here the curves are computed, and any fine-tuning and model validation is made at this stage, and then the machine is commissioned in RayStation, and it's ready for use within the treatment planning software. So I hope I didn't talk too fast. I get excited when I talk about great things, when I talk about RayStation, when I talk about tomotherapy, and also MCO. So how about we go ahead and take a look and let's see it. I've brought up a plan here. And when we were talking about the use of MCO, I just want to point out here that you can see that we have our trade-offs and objectives selected. Here under the constraint side, I simply put in targets. I hadn't created or added any other structures, but you certainly can. On the left here, under the trade-off objectives, I entered in all of the structures that I want to obtain a slidey bar on, okay? I utilized the max EUD of 0 centigrade with varying A parameters, as well as uniform dose, and unique to RayStation is a dose fall-off function that we can apply to the external. And so I also put those in. When utilizing those, they can act as rings where we can really tighten up conformality of a plan. Another use for it is for some of the low dose out in the periphery, we can kind of tighten that up and bring that in as well. And putting that in the objective side here really gives us the opportunity to create that slider and see where it goes. Once we've generated our Pareto plans, we end up in our navigated state. And this is where we now have our slidey bars. You can see here on the right, I have put in the right bottom corner here, I've put in clinical goals. These should be predetermined by you. These are your check sheets for your physician, your Quantac, whatever it is that you use. These can be built within RayStation as templates and readily available for any treatment site. And the nice thing is from this point on, in this navigated state, let them guide you. Let them be what helps us determine whether we have a good plan or not. So you can see here the green ones are satisfied and our orange ones we need to work on a little bit. And what I tend to do is I start off with those important ones, my serial structures, if you will. So we'll go ahead and take down here, I'm just going to slide the spinal cord here. Left thumbs up is better, lower dose, and you can see as we slide, it will turn green. I'm going to go ahead and clamp that down right here just to show you what that does. You notice that everything kind of has, a lot of these slidey bars has turned gray. And what that's done is it's tightened up our solution space or locked it down. This is space that's no longer available based upon the choice that I made. The next structures we can work on, of course, we can walk through our parotids and we can slide those down until they give us what we want. Get that down, and we're going to go ahead and lock that as well. We can work on our right parotid. Once everything's green, you can see if you look in the sagittal view that I do have some of this dose perhaps back here in the posterior neck. And this is where you can also take these dose fall-offs and bring that down and take that, and you can see here that it just brings that dose out of the back of the neck. Once we have navigated our plans and we've really decided where we want to be and that it's accepted everything and we're green, of course, we would just do that final computation and develop our deliverable plan. I'm going to bring up our deliverable plan here, and what that's going to do is we can look at it, but also I want to show the comparison that it is very close to, if not identical to, the lines that we saw before, okay? So really what you slide is what you get when you're doing the deliverable plan in the tomotherapy module. Our clinical goals remain green. We're here, we have everything we want. This is, at this point, a fully deliverable plan. If we come to plan design, I just wanted to show you some of the visual aids and aspects that I had kind of explained in the PowerPoint and in the slideshow. So here, if we turn the visualization on, we can play this animation. And once we do that, you can see here, make this one bigger for visualization. What this is doing is showing where those are as the patient modulates or traverses through the machine. We're able to see this modulation and the beam open and close time. The other thing that's nice to show here is as this patient's going through, you now see that we have this plan set at dynamic jaw, and you can see it opening up as it grows. We're using, or as it goes into the machine, we're using a wider, the bigger jaw through the length of the tumor volume. This will just help us with treatment time. Again, you can see that in all three views, in the axial, the coronal, or the sagittal plane, as well as if I turn the room view on, you're able to see it as a nice just visual aid of how this is rotating around the patient and how we're able to use this here. Let's go ahead and turn that off. So the main goal here is just to show you that we have this integrated workflow. It's one control center for all your treatment planning needs. There's flexibility in planning on one system to be able to change or combine treatment techniques and modalities if we need. Some of our very advanced features such as MCO, adaptive, and fallback planning bode well with tomotherapy planning, as well as our first user-reported validations are very positive. Our plan, we do have our friends at MCI, which is the Miami Cancer Institute, who are currently in their validation process as well. They're doing a lot of tomotherapy plans on the RayStation platform and actively searching out that first individual patient that they can use for treatment. And for further information regarding any TOMO planning or RayStation, please contact us. I think you can tell I like to talk, perhaps too fast and too much, but I'm excited and happy to show you more at any time. I think we still have a few minutes left of this presentation. I'd like to go ahead and go back to Tammy, and she can open this up, and maybe we can touch base and answer a few questions that have come in.
Well, thank you very much, Misty, for a really interesting presentation. As you say, we're now going to take a bit of time to look at some of the questions that have been sent in. So, first question that I have for you. Do tomotherapy MCO plans need to be converted?
So, that's a good question. And the answer is, because I did allude to the fact that this is deliverable dose that you see while we are sliding. But the answer is yes. Because of any open leaf change or the possibility of a rounding issue, we do a final calculation in CC, which will help us to seat that deliverable plan. Is there another one? Sorry, Jessica.
Yep. The next question, in the optimization phase, does RayStation perform all optimization steps in full scatter?
I'm sorry, you broke up just a little bit. Are you able to repeat that for me, Tammy?
Yes, sure. So this is a question, in the optimization phase, does RayStation perform all optimization steps in full scatter?
Eric, can you answer that perhaps? Because I'm going to say yes, that it is in the optimization phase. We are taking into account the algorithm, of course, takes into account all of our densities. And then when we create our deliverable plan in the CC convolve, it is taking that into account.
The dose algorithm used during optimization is not as accurate. It's a fast dose engine, right? The singular value decomposition algorithm. So the final dose will be, the clinical final dose will be, of course, be more accurate than the dose computations during optimization. But that's standard procedure in all types of optimizations in RayStation.
Okay, thank you. That is Eric Sterner from Research, who is also going to be answering some of the questions for us. So the next question we have here, does the MVCT DICOM export to RayStation include the frame of reference? So in other words, does RayStation recognize the setup correction applied to the couch?
Yes. Once we've exported that through the IDMS, that will be available, as well as I think that bodes very well into the adaptive planning and the ability to see that. So it will be and can be exported, and those shifts are applied. So anything, the daily shifts we've made, kind of like our cone beam CTs now, if you send those in to the system, we will recognize that shift.
Okay, and there's another part to this question being sent in by the same person, which is, does the DQA functionality in RayStation support movable red lasers to be able to position the phantom on the most optimal measurement position?
Oh, that's a great question. I'm going to have to defer to physics on that, because I'm going to say yes. that we would defer to, or that we would export those movable red lasers because it's the same positioning as the patient. Do you know that, Eric?
Well, there is no automated way of positioning the red laser in an optimal way, but the user can define the setup manually or graphically, and the positioning will be automatically used when delivering the measuring plan in the same way as for the treatment plan. So basically you can make sure that the dose in the phantom will end up at the spot where you want it to end up. Was that an answer to the question?
Okay, thank you. Another question, is Monte Carlo calculation available yet?
Coming version. So not currently in RayStation 7 is there Photon Monte Carlo for the Tomotherapy platform. This will be available in RayStation 8.
Okay, great. Next question. It looks like that while IDMS is required to bring in my exact machine parameters, I should be able to use the standard model just to play with the planning without having IDMS. Is that correct?
The standard TOMO machine, like I said, to play with the model in RayStation from...
I guess so, without having IDMS.
We could provide a stock machine or a TOMO machine, but it wouldn't be your clinical machine. We would need IDMS to bring that across and to build a model on for planning purposes.
Okay. Related, do you need to have precision software with IDMS?
So you do not have to have precision. We just need to have IDMS because IDMS offers that gateway. So tomotherapy planning in RayStation still has to pass through IDMS to the treatment planning console. So no, you would not need precision treatment planning system. You would only need the IDMS. That is possible.
Okay, thank you. Just a quick shout out to the audience. We're in the last few minutes now, so if you do have any more questions, send them in now. Next question for Misty. Did you say you can create a plan for a conventional linac from a TOMO dose distribution? And if so, how do you combine these?
So yes, you can, and that is in our fallback planning where we use that dose mimicking algorithm. So you can take any dose and import it into RayStation. So yes, we can take a tomotherapy plan dose distribution and create an IMRT or an SMLC plan, and vice versa. We could also take that and transfer it with the tomotherapy planning module and be able to create a tomotherapy plan.
Okay, I have a two-part question for you now. So the first part is, where does the plan approval take place? Is that in RayStation? And how do you suspend previously approved plans?
So there is an approval in RayStation, but in order to deliver the machine, so once the plan has been done within RayStation, that tomotherapy plan is transferred to IDMS, where there will be an approval on that console, and then treatment delivery is available on the tomotherapy machine. And what was the second part, Tammy? My apologies.
Sorry. How do you suspend previously approved plans?
On the tomotherapy side, that would just be an unapproval of that plan, because the only plan that you're able to deliver, in my recollection, is the only plan you're able to deliver is one that is approved. So if it was previously approved, you could invalidate or unapprove that plan.
Okay. Can you have both RayStation planning and TOMO plan, not precision, but the prior version, running through IDMS at the same time?
I'm not sure I understand that question, Tammy. Can you repeat it? If you can have a prior TOMO plan and...
Can you have RayStation planning and TOMO plan running through IDMS at the same time?
That's a good question. I am not really positive of the answer to that. That's one, if you can please take down the user's name, I'm happy to definitely find out the answer to that. And
absolutely. Yeah, we can respond to questions afterwards if you like, and go into more detail. Yeah.
Okay.
Great.
Yeah, because that gives us the opportunity to, I'm happy to reach out to anybody who has more interest in this, or if there's a question that perhaps we didn't get to, or maybe if you didn't feel that we gave you a very detailed explanation, I'm happy to dig in with our partners at Accuray as well as, development in Stockholm and find, the correct answers.
Excellent. Okay, in the fallback plans, does RayStation show the difference in DVH between the fallback plan and the TOMO plan?
Yes, it shows the differences in DVH as well as any of those clinical goals that you have. It shows them as red and orange, whether they were met. So if you can tell if you had a plan that all of those clinical goals following along with the DVH, if that was previously accomplished, and then if the fallback plan is not accomplishing it in the same level. So yes, those are available for review.
Okay, can you copy plans?
Absolutely. That's the glory. You can copy plans. Any of the functionality that you have within the RayStation platform can be used with this modality of tomotherapy planning. So we can have the ability to show dose on our additional data sets. We can use this dose and combine it with other plans. And yes, you can copy this plan and, further optimize if you so wish, just to see if you can further decrease an organ at risk or whatnot.
Okay. Does RayStation allow adding more fractions later to a plan? That is, say the doctor wants to add 3 fractions after the patient is already under treatment.
So yes, in RayStation alone, of course, you can do that as a summed plan. And in the Tomotherapy platform, you would just simply be able to export this plan via IDMS, and you could add additional fractions.
Okay. Someone has asked here, how does fallback planning deal with very long target volumes? Is it with multiple isocenters on conventional linacs?
So when you create a fallback plan, I believe initially it is a single ISO center. So that would, the initial plan, so if we had using protocols, I'm certain that we could set up the ability to have 2 ISO centers. That one might take me a little bit of practice. I would have to look into that a little bit. But you could create a protocol with 2 ISO centers, and I think that would do a good job of delineating, 2. I would say we'd have to separate out those PTVs into 2, maybe an upper or lower, if you will. But yes, it can be handled.
Okay. Interesting comment here. Since CyberKnife and Radixact share the same database, will there be capability available to use MCO for CyberKnife soon?
That is not current in RayStation 8. It is in the works. I'm not exactly sure of that roadmap, but I would anticipate that is coming.
Okay. Great.
Eric may be able to better answer that from a development standpoint, but I do know that we are in works and continue to work with Accuray and being able to offer these platforms under one treatment planning system.
Yeah,
okay.
You might add that is work in progress in the research department at RaySearch.
Great.
Excellent. Right. Well, we're coming to the end now, so just like to say thank you to everyone in the audience who asked a question. As we said, if your question wasn't addressed or is going to be answered in more detail, you'll be contacted by email with an answer. If anyone would like to watch the webinar again or recommend it to a colleague, it'll soon be available on Physics Connect or on the Medical Physics Web's multimedia page. Finally, if you haven't done so already, please can you rate the webinar using the ratings button on your screen. So finally, thanks again to Misty. Thank you to everyone who has joined us today. This webinar is now over.